You live in the US in 2015, and there's a roughly 1 in 3 chance that your health data was a subject to a data breach. That basically means that there's a high probability that some of you listening to this recording had your data exposed to hackers. Well, some of these attacks could have probably been avoided had we built more secure data systems. I'm Kajetan Maliszewski, and today I'm going to discuss if we can use secure hardware to build more secure and privacy-preserving systems. I present the paper, What is the Price of Joining Securely, Benchmarking Equi-Joins in Trusted Execution Environments. This is a joint work with my awesome collaborators. So when we think about data, we think of 3 states of them, and that is in transit, at rest, and in use. And each of these states requires a set of special protection techniques. And today we're really good at protecting data in transit and at rest, but we are still missing ways to efficiently protect data in use. So in a public cloud scenario, like here in the slides, we basically know how to send the data to the cloud. We can store it encrypted, so far no problem. But then when we start processing the data, that's where it all gets exposed. And so hardware manufacturers propose trusted execution environments as a potential mitigation to the problem. TEEs is basically like deploying a black box inside of the CPU of a remote machine. So now the cloud administrator can look at the black box from different angles, can touch it, knock on it, but they will never really understand what's happening inside of the black box. But the real challenge with TEEs is, as with every modern hardware, that they have their peculiarities and they introduce some new and sometimes unexpected bottlenecks. And these bottlenecks can be pretty severe here. So we have this secure cache that is somewhere between the L caches and the main memory. We have a very expensive interaction with operating systems. So operating system calls now are untrusted and expensive. And we have new SDKs, which basically force us to rewrite some of the code. So there are really doubts how large data systems would run in these environments. In this paper, we answer those questions for relational Equi-Joins, because joins are ubiquitous and expensive. They are also notoriously complex, yet they are crucial to the analytics we do. So for example, TCP/H query 2 has 8 join operators in its plan. And then early on, when playing with TEEs and joins, we realized that things are very different there. You run a simple thing like a hash join, and you have 2 or 3 orders of magnitude performance degradation. So we said, okay, we need a benchmark for it. And that's what we did. We benchmarked a wide spectrum of different join algorithms in very different dimensions. And we present lessons learned. We talk what to do in the paper, what not to do to efficiently process data in trusted execution environments. Okay, so which algorithms did we benchmark? We identified 8 core algorithms, which would split into 4 families. So we have hash-based joins, we have sort-merge joins, radix-based, and nested-based. And in those 4, in between those 8 joins, we have more textbooks, like textbook joins, and then we have more specialized modern designs. Okay, which tool did we use to perform the benchmark? Well, we didn't find any tool that would allow us to conveniently benchmark different relational operators in different TEs. So we wrote one, and that became the first contribution of the paper. TEEbench is a unified framework that allows the users to seamlessly connect their relational algorithms and seamlessly run them on different TEs. So we had this plug-and-play philosophy. We're designing the framework. So users pretty much just provide the implementation of an algorithm. They can use our API for some more sophisticated measurements. Then they decide do they want their data or generated data, and that's it. TE compiles the code and runs it on any TE. We used TEEbench to run pretty much all of the experiments in the paper, both on Intel and AMD architecture. Okay, we know the why, the what, the how of the benchmark. And now time for the lessons learned. So actually the results of the experiments. We are only going to touch on 4 aspects. All the remaining, because we don't have time to talk about all of them, for all the remaining, I invite you to check out the paper. Okay, lesson 1, fit your data structures into EPC. So we now have this memory model with a secure cache called EPC somewhere between the L caches and main memory. It's logically between them. Physically, it's in main memory, but it's still like it's still data from L3 goes to EPC and then to main memory. So when we exceed EPC, we start to page out to main memory. And this paging is extremely, extremely expensive. We know it's expensive from Intel. We know from related work, there have been approaches to estimate the cost of a single EPC miss, but we are really the first ones to actually rewrite a little bit part of the kernel to extend the kernel driver and to report the EPC misses to the user. And so we present the results in the figure to the right. We see there the throughput and the number of EPC misses of one of the hash joins as a function of the size of the outer table. And so we see that as we increase the outer table, the throughput gradually decreases because we hit new caches. But then we reach the end of EPC, we see a spike in EPC misses, and we see the throughput goes virtually to 0. So we virtually kill the algorithm. And that's because EPC paging is just so expensive. It completely takes over the execution time. So lesson 1, fit your data structures into EPC. Lesson 2, Mutex is the new bottleneck. Threads are inherently served by the operating system. And as I've already mentioned, this interaction between enclaves and operating system is now very expensive. So we took the algorithm, the join algorithms, and we measured their throughput while scaling up the number of threads. And we see in the figure to the left that while some algorithms actually have a relatively okay scalability, some of them scale only up to 2 or 3 threads and then completely go down. And that's because the interaction between the enclave and the operating system becomes a bottleneck. So we took radix join and we said, okay, how do we avoid some of this interaction? We re-implemented it. We took out all the mutexes and we replaced them with spin locks. And we see the results of this experiment to the right. We see that our mitigation helped in this situation. We have a decent scalability now for radix join as well, but it's not a solution that fits all the scenarios, right? You can't suddenly block all the threads. So we consider multi-threading as still an open problem. Lesson 3, use less memory during data execution. This lesson really refers to secure computation because there eventually your input and output data will be encrypted. So we wanted to also measure it. And we measured the joins. We split the measurement to the actual cost of the join, data materialization, and data encryption. And we report those results in the second column of the triple. And we see that we confirmed our intuition for high join selectivities. The costs are really, really overwhelming. So we took a step back and we looked at it from the data movement perspective. And we applied one of the techniques used there, that is data chunking. So instead of accumulating the entire output buffer, encrypting everything at once and sending it out, we now define a smaller one. And once the buffer is full, we encrypt it, we send it out, and we fill again the same buffer. So we significantly reduce the memory consumption. And now we measure the total encryption time as we increase the size of this buffer, and we see that we have the best results when the buffer is actually just below the L3 cache. So we took this minimum, and we repeated the experiment, the first experiment, now with chunking enabled. And we report the results here in this third column of the triple. We see that we managed to significantly reduce the encryption costs, And overall, the throughput, we improved the throughput by up to 40%. So lesson 4, more throughput is not always better. So some people come to me and they say, Kajetan, why do you even benchmark this? Why do you make things complicated? Everyone knows that the enclave from AMD has a performance similar to the plain CPU. And they're right. We actually took the TE technology from AMD, we benchmarked it, and it turned out that the performance is similar to plain CPU. But what these people don't know is that AMD provides very different security and privacy guarantees. They actually sacrifice some of the guarantees in order to improve their performance. Why do they do it? Well, that's their design decision, but they do not provide integrity protection. And moreover, they put the entire operating system inside the TE. So now you have to actually trust that the operating system has no security holes. So although the throughput is higher, well, we still see this direct comparison as comparing apples and oranges. So all of these results, they basically show us that there's no clear winner between the joins. None of the algorithms fully exploits the potential of TEs. And this last figure really summarizes our findings. So here we present the CPU cycles per tuple cost of each of the algorithm. We split it between different phases of each algorithm, and we immediately see that some operations take insane amount of time. And these operations are like probing a large hash table or accessing a large index. So we really conclude here that there's no clear winner, but we also we see the cost of these operations, but now we know why these operations are so costly, because we just talked about EPC paging, we talked about mutexes, so we conclude that none of the algorithms really fits entirely the architecture of TEs. Yet, if you still have to choose something, we recommend hash-based joins for data that fits the secure cache, and radix-based joins for data that does not fit the secure hash. And in general, as a rule of thumb, you would want your data structures high in the memory hierarchy, so at least in the secure cache, and that's even more important than in traditional CPUs. So we have seen that TEs have the potential to provide high privacy and security guarantees in the public cloud. We have seen that none of the existing join algorithms really fits trusted execution environments, and therefore we call for TE native algorithms because we think that this community is the right place to address this problem. For more details, I invite you to check out the paper and the QR code over here that will take you to our GitHub page. So we believe that TEs will become someday the default way of computation in the public cloud, because remember, the future is confidential.